6 review. I'll make this into 2 videos, chapter 1 through 9, and then 9 through 18. I'll break it down. Okay, so in this first part, all you're doing is just rewriting from exponential form into logarithmic form. And I want to rewrite this one, 6 raised to the 4th equals 1286 into log form, and just write the answer right here. Okay, and then it should match one of these. Now, I believe this one is off. That one should be log of 8 of 1/64 equals -2. Okay, so when you switch forms, when you go from an exponential b raised to x equals y, that switches to the base stays the base as the log, so b stays b, and then whatever's on the same side is no longer on the same side. So b and x are on the same side, so when I switch on this one, they're no longer going to be on the same side, so y must go here and x goes here. So basically, follow those 2 rules. You can go from log to an exponential or from an exponential to a log, vice versa. So base is 6, so that means the log, the base of this log would be 6, and then 4 is not going to be on the same side as the equal sign as 6 is, so it has to go over here, so that means 1296 would go there. And then this one, 24 is the base, so that's the base of this one, and they are not going to be on the same side, so 3/5, and then 27 would go there. Okay, and then here this last one, base is 8, so the log is going to be base 8, and there is no log of base 8 in this thing, that's why I had to rewrite this one. And then -2 is with 8, so it's no longer going to be with the 8, and 1/64 would go there. Okay, evaluate the log. This is the same thing. I want to rewrite that as an exponential, but this time there's no equal sign. So if you want to, you could just add an equals x on it and then rewrite it. The base is 81, so going backwards, if this is my base of the log, it's going to be the base of the exponential. So 81 is going to be the base of the exponential, and then whatever's on the same side will no longer be on the same side, right? So since 3 is on the same side with 81, it's no longer going to be on the same side with 81 when I switch forms. So that means x, or the answer, has to be as the exponent. Now, how can I rewrite this? Using the same base, right? So I want to rewrite 81 as 3, that same base 3, raised to something equals 81, right? So I can just take 3 and times it by itself so many times and see if I get 81. That would be a 4, right? So that would be a 4. 81 can be rewritten as 3 to the 4th. So I can take 81 and rewrite that as 3 to the 4th. So that 81 is being raised to x, so this 81 would be raised to x. And now, since the bases are the same, 3 and 3, I can now set these exponents equal to each other. But when I raise powers to powers, I multiply, so that'd be 4x equals 1. Solve that. So I get x equals 1/4. And that would be my answer. Then I can put that on a calculator. Okay, this next part's a little bit different. So this is asking us to solve for k as the base. Okay, so k is the base, and it gives us this point 16, -2. So that would be our x is 16. So I could just plug that in for x. And then it gives us a y of -2. Well, that's my f of x, right? So that'd be -2. And then I have subtract 3 after I take 16. That's why it's in parentheses here. That x is in parentheses. And so now I can just solve this by getting the log by itself first. So I add 3 to both sides. So I get 1 is equal to log k of 16. Now I can switch just like I did the previous problems, right? Switch base of the log is the base of the exponent, and whatever's on the same side is no longer on the same side. So that means the answer of the log is the exponent. Now I can solve this problem, right? K raised to what is 16? Well, that's just 16, right? 16 raised to 16 raised to 1 is 16, so k is 16, so this is base 16. So normally what we usually see is we don't see the k there. Sometimes we usually see the k here, or sometimes we see the k inside the parentheses, like x minus k or something like that. Take the log of that, and it gives us some base like 4 or something like that. Right, so there what you want to do is just, normally in a logarithm, it looks like this, right? And it always has this point right here. So log with any base of x is always going to have this point right there, and that point is 1 comma 0. Because if I put a 1 here, the only thing b raised to what is 1, that would be 0, right? Anything raised to 0 is 1, so that's why we always get this point 1, 0. So whenever I take the log of any base of 1, my answer is always 0. So I get this point 1 comma 0. So you just look at that 1 comma 0 should be there. Well, where's this one? This one is down 2, down 3. So that's why this says minus 3. So if you have a different problem that the k is not as the base, but the k is out here, or the k is in with the x, then you can track this point. How does this point move? Does it move down, up, or down? That's going to be on the outside after the log. If it moves to the right or to the left, that's going to move on the inside, but it's always opposite on the inside. Okay? So that's kind of how you can track it. If your k is the base, then you kind of have to do it this way, that one is. Okay, so there you go. If it's different k, if the k gets moved out here or moved in here, then you can do it that way. All right, this one here, a master graph, and I'm really doing the same thing here. I'm using this fact, the log of any base, even 4, of 1 will equal 0. So what gets me a 1 in here? Well, what would give me a 1 in there is 1, right? So if I plugged a 1 in for my x, then this right here would be 0. 0 times a negative is 0, and 0 plus 2 is 2. So I should have a point 1, 2. So I look at a point 1, 2. 1, 2, maybe right there. 1, 2, nope. 1, 2, okay, right there. And 1, 2, nope. So I know it's not those two based on that. And then traditionally, I know a negative out front is going to flip it. So like I said from the other graph, normally it looks like this, right? It has this vertical asymptote through here, and that's always what makes this 0. What makes that 0 would be undefined. Okay, so that means I should have a vertical asymptote at 0, which I do here, and I do here. So both of those still play. Now this right here traditionally looks like this, but this negative out front is going to flip my answers, right? So it's going to take this graph, and that negative log is going to flip that, and now flip it over the x-axis to look like that. So this one would be our answer right there. Instead of, sorry, I meant to cross out this one, I guess. This one. And so because this is not flipped, it's not that one either. Okay. All right. Number 5 here, just basically just solving this problem, rewriting it. It's a log, so I can solve it by rewriting. My base is 32, so that's the base of my exponent, right? Remember, log of any base of x equals y gets switched to the base, stays the base. Whatever's on the same side is no longer on the same side, and the answer of the log is the exponent. Okay, so that means the answer, 7 over 5 would be the exponent, and x would be the answer of the exponent, because these two are no longer on the same side. Okay, so now I can just answer this. Remember, any type of fraction as a fraction as an exponent is a root. The bottom is the type of root, so this is the 5th root of 32, or what times itself 5 times is 32, that'd be 2. And then the exponent, the numerator, is still an exponent, so it stays as the power. So 2 to the 7th is 128. 128. So you just rewrite it, and then you can do fractional exponents. The bottom is the type of root, what times itself that many times, and the numerator is still the power. Okay, this one, whenever the logs of the bases are the same and the equations are equal, that means what I'm taking the log of also must be equal. So I set them equal to each other. Now this is a quadratic equation. We solve that by quadratic formula or graphing. We could do a y1 and y2 and see where they intersect, or I can set it equal to 0 and just do a y1, or I can try to factor it. Our a is 1, so that makes it easy. Our b is negative 23, and our c is negative 108. So I could ask myself, or I could just plug in these numbers and see which ones work, which ones are true, right? And it says select all that applies, so I kind of got to be careful here a little bit because I can't take the log of a negative. So if I plug in a negative x, that's going to give me a negative, so I know a negative answer is not going to work. Okay, so we could cab this. It is cabable or factorable. Okay, you could do quadratic formula or you can graph, but the negative answer is not going to work. And negative 23. So that means what times what is 108 but adds 23? Well, I already kind of know the answer. That's negative 27 and a positive 20 and positive 4, because that will subtract a negative 23. And I divide those by my a, but my a is 1. And then I take the opposite, right? Because this x minus 27 is a factor, and x plus 4 is a factor because they equal 0. And then I just take the opposite, so x equals 27 and x equals negative 4. But negative 4 is not going to work because I can't plug a negative in here because I can't take the log of 0 or any negatives, right? So this is my correct answer there. Okay, this problem is probably more complicated for you, but we want to use the fact that log base 3 of 7 is approximately 1.7712, and we want to use it to approximate this number. Log base 3 has the same base of 15,309. So what I just want to do is I just want to break down 15,309. So I want to break that down into factors of 3 and 7 because I know two facts. I know that log since log base 3 of 3 equals 1, and log base 3 of 7 is approximately 1.7712. If I can break this down to 3's and 7's, then I can just be adding 1 and 1.7712. And 15,309 breaks down to, let's break it down to a factor tree. So if I divide that by 7 or 3, I divide it by 7. I get 7 times 2187. I could break that down by a 3. Let's see, divide that by 3. We get 729. 729 kind of looks familiar, like some factor of 3. It's 243. And that definitely looks familiar. That looks like 3 raised to something, like 3 raised to 5 or something like that. So I can keep on dividing by 3. So 3 and 81. Oh, I know 81 definitely. 9 and 9. 3 and 3 and 3 and 3. So it's a factor of 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6, 7, 7, and 15,309 breaks down to 7 3's and 1 7 1 7. So that means if it's 7 3's, that means I'm taking log base 3 of 3 7 times. That means I would be adding 7 1's. So 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1, 7 3's. And then it has 1 7, so that means it's a 1 log base 3 of 7, so that means I would be adding 1.7712, which would equal 8.7712. Okay, so that's how you break these down. You look for factors of what you are given, the base, and what you're taking the log of to approximate bigger numbers, because we know when we are multiplying two numbers, I can rewrite that as the addition of two logs, right? The addition of two logs. So that's why I'm adding 1 plus 1 plus 1, because I'm taking this log, log base 3 of 3, and adding log base 3 of 7. But I have 7 of these, so that's why I have 7 ones. Okay, so hopefully that kind of starts to make sense. You just break the bigger number down to factors because you know you're adding those logs together. Okay, this part, some stars appear brighter than others because they're closer to the Earth. The equation m equals little m plus 5 minus 5 log 10 base 10 of d can be used to determine the absolute magnitude big M. So the absolute magnitude is big M given the apparent magnitude of m and the distance d. So apparent magnitude is little m and the distance from Earth probably is d. And so we want to find out which one of these are closer. So here's my little d and here's my little m, and basically I just want to plug those into this equation to find the absolute magnitude. So I want to plug in 7.76 for my d into this equation and 0.03, make sure I write it correctly, 0.03 in for my little m, so plus 5 minus 5 log 10 base 10, that's in my calculator, so that's just log in my calculator, and then that distance of 7.76, and then I want to plug in 0.38 in for that apparent magnitude into this equation with the distance of 3.51, and lastly I want to point in apparent magnitude little m 0.85 plus 5 minus 5 log the distance of whatever that one's name is. That distance is 20 parsecs, or however you say that as well. I want to plug these in and see which one is the largest. Okay, so I calculated those in. Vega is 0.58, Procron, however you say that, I don't know, it's 2.65, and then Aldebaran, I don't know how to say that, is negative 0.66. So the largest magnitude is the Procron. I don't know how to say that. Okay, so that is the largest magnitude. So that's just plugging in numbers into a formula and taking the log. So make sure if it's just log base 10, that's just log on your calculator next to the 7 button. All right, solving. Remember, we normally try these the same base, like that one problem we did, like number 2 or something like that. Okay, well this one, what I want to do is take the log of both sides. So I take the log of this side and the log of this side. So it looks like this, log of 14, and 14 is being raised to x minus 5. Now the properties of logarithms say that if I have a log of something being raised to the exponents, that I can just multiply the log by that exponent. So I can rewrite this as x minus 5 times the log of 14, which is really just some number, equals x log of 8, which log of 8 is just some number. And we want to match, is that any one of these ones in here? Right there. That's not that one, because that's 8 times x. The x needs to be in front of log, so it's not that one. Okay, and then we can distribute this log to both of these numbers. So that'd be x log 14 minus 5 log 14. So look for that in these answers. Is that in there? Doesn't look like it. Okay, now our goal is basically to get our x's by themselves, right? Because this is like, say, 24x and this is like 13x, so I want to move those over to the same side, right? So I'm going to subtract that x log 14 over. And you could move it either way. I think this one actually moves it to the other side. So this one actually moves this one over. So minus x log 8, and then it moves this 5 log 14 to the other side. So it likes positives instead of negatives. That's why it's doing that, but it really doesn't matter. Just if you have negatives, you can multiply top and bottom by a negative, and that just switches all the signs. That's what you have to be careful with. because I believe it's one of these two is one of our answers as well. All right, so then I can go ahead and simplify that, and so this becomes x log 14 minus x log 8 equals 5 log of 14. Now I have x's on my same side. All right, so notice I have an x in both of these, so I can factor out an x. Now I'm just down to 1 x instead of 2 x's. Right, because my goal is to get x by itself. Again, this is not in our list, so I can keep on going. Divide, right, because this is being multiplied, so I get rid of it by division. Log 14 minus log 8, and divide by that. So this is our answer. Look for that in our list. Minus log 8. So if you had a negative here on top, a negative and a negative, that's the same answer. So this would be the same answer as this with a negative there. Okay, and so that's in our list as well. It is right, positive 5, 14 log, and a 14 minus, so it's this one. Okay, so this is not that one. Okay, now what you got to be careful is too, when you enter this in a calculator, you need to put parentheses here, and parentheses here, right? So we can enter that in, and I believe we get positive 23.579 in our calculator. And so there is our other answer that is shown to be correct. Okay, so you had a possibility of 2 in there. And so you take the log of both sides, any exponents go out in front, you multiply the log by those two, get your x's by themselves, then factor out the x and divide by what's not x. Okay, and if you have a negative on top and bottom, you can multiply everything by just a negative. Okay, so that's it for the first part of chapter 6.